All right, before we move on to the next set of examples, we're going to take a quick look at this theorem, so-called the p integral. So really, this is just a very common result that we're going to use again and again throughout these sections on improper integrals. And then when we move into sequences and series, in particular series, we're going to use a result that is similar, although it has to do with a series, not an integral, the so-called p-series. So what we're looking at here is, excuse me, integrals of the form some starting value, a, to infinity, of a function 1 over x raised to some power, p. Okay. So, geometrically, what this means is we've got our axis, and functions of this form 1 over x to the p, if p is positive, it's not negative, since p is already in the bottom of a fraction, if p were negative, then it would really move to the top. So 1 over x to the positive 2, for instance, this is rightfully belonging in the bottom. So in general, for p non-negative, or excuse me, for p positive, I should say, all these functions look something like that. The bigger p is, the more steep this transition is, the more rapid it is. But here we're going to be integrating from some value a all the way to infinity. So this integral represents the area from a to infinity. So you can pause this video if you'd like and take a look at the proof. I walk through it line by line. But for us, the proof in and of itself is not the important part. The important part is how we're going to use this result to, together with the comparison theorem, to help us determine whether or not lots of different improper integrals converge or diverge. So the main takeaway from here is that this integral converges if p is greater than 1, and it diverges if p is equal to 1 or if p is less than 1. So the area under the curve is infinite in those cases, and the area under the curve, if p is greater than 1, depends on the value of p and the starting value a. So for instance here, if I had the integral from, let's say, 4 to infinity of 1 over x to the, let's do third power, 1 over x cubed. Since p is equal to 3, which is greater than 1, I know that this integral converges, and it converges to this value, a to the 1 minus 3 over 3 minus 1. And what's a? Oops, should have plugged that in. A is 4. So this is 4 to the negative 2 over 2. So this is 1/16 times a half, 1/32. That is the area. Okay. Let's take a look at this example 5. Determine whether the following integral converges. If it does, determine its value. So here we can see that our a value is 1. But remember, this value a, that doesn't determine whether the integral converges or not. That's just going to change the value of the integral if it does converge. So that would really influence to what value the integral converges, if it converges at all. What determines convergence is really the value of p. So first look at the p value, 2. So 2 is greater than 1. And let's erase that a for now. So p is equal to 2, which is greater than 1. So this means converges. Since the integral converges, that means it approaches a unique real number. So what's that real number? Well, from the p integral theorem, we can say that this is a to the 1, or sorry, our a value is 1. So 1 to the 1 minus 2 all over 2 minus 1. So this is 1 to the negative 1 over 1, which is 1 over 1 over 1, which is 1. So this has area 1. Okay, example 6, again, same question. First, look at your p-value. Here, our p-value is 2/3, which is less than 1. So this means the integral diverges. And we can be a little bit more specific, and we can say it diverges to infinity. Because there are different ways that an integral can diverge. It can diverge because the value of it approaches a infinite quantity, like negative infinity or positive infinity, or it might just not settle on a unique real number, such as the area underneath this graph. As I go farther and farther down the line, doesn't matter where I start, I could start at x equals 0, so then the area here in red will sort of get canceled out by all these blue areas, because from 0 to 2 pi right here, pretending I'm a better artist than I am when I just freehanded this, the areas here are actually equal, again, if I were a better artist. So from 0 to 2 pi, the area is 0, but if we go from 0 to pi, the area is whatever this is. So really, the area here would always be oscillating and changing. It never settles or hones in on a specific, unique, real number. And that's why, in this case, that improper integral from 0 to infinity would diverge. So we can diverge for different reasons. In this case, it actually is going to just tally up to infinity. Okay, example 7, same question. So here, this looks different than the regular p integral. So I'm just going to comment on that. So it looks different than our basic form for a p integral, which is a to infinity 1 over x to the p dx. So it looks different here. So first what we want to do is change it so that it looks like this. So we can change it by performing a u substitution. So by substitution. Specifically, we can let u equal x minus 1. Then du is dx, and our bounds, u of 0 becomes, what, negative 1? And u of 3 becomes 2. Oops. So this becomes the integral from negative 1 to 2, 1 over u squared du. Now notice here, we changed part of it to match. What was just 1 over something raised to a power, we now have that. So that's good. We did have x minus 1 then raised to a power. We eliminated that, and we just have a single variable raised to that power. But notice here, our bounds. We are beginning at a finite value, but we are going to yet another finite value. So this one is a bit strange. Okay. So, since the integral that we have, the bounds in particular, make it sufficiently different than this. There's not an easy way for us to just introduce an infinity here if we're not actually going to infinity. So it looks like we can't use the p-integral theorem as we know it. So this means we're going to have to proceed by direct calculation. So and by directly calculating, I mean we're not going to rely on that theorem because the theorem doesn't apply. But we can go ahead and actually calculate this. So first thing we're going to do here is, it might not look like anything crazy is happening here, but there is an issue. So there's an issue with the fact that our integrand in particular, our integrand has an infinite discontinuity at u equals 0. Notice that 0 is contained in the interval from -1 to 2, and as u, our variable, approaches 0, 1 over u squared approaches infinity. So there is an infinite discontinuity. That's the issue. So, much like before, our problem was infinity. So we used a limit as our variable, as our parameter r goes to infinity, and we could replace that and then proceed as normal. Well, that's exactly what we're going to do here, but the problem isn't infinity. The problem is an intermediate value between -1 and 2, the value of u somewhere between here. So what we can do is well, first of all, we'll actually have to break this up into the integral from -1 to 0, 1 over u squared du, plus the integral from 0 to 2, 1 over u squared du. We're going to break up our integral at that problematic, because right now we can't do what we did before with this kind of integral, where we had the problem value of our variable in the bounds. Here we do know that it is contained in this range from -1 to 2, excuse me, but it's not present as one of the bounds up here. So to do that, we split the integral so that the problematic value of u becomes the bounds. Then, in the next line, we're able to introduce the limit. So we're going to do the limit as r approaches 0 from the left for this first integral, plus the limit, oops, sorry, not 0, I should have an r up there, plus the limit as, let's say, I don't know, let's say q. The limit as q goes to 0 from the right of the integral from q to 2. One over u squared du. Right. So integrating this, for each of these we have the same antiderivative. It's going to be u to the -2. That's going to integrate to -u to the -1, or -1 over u. So this would become -1 over u. So let's move that negative sign out front. And again, plus, but we're going to have this antiderivative is going to be -1 over u. So it'll be minus the limit as q goes to 0 from the right of one over u. Now we need our bounds, so let's make room for that. This first one has bounds from -1 to r, and the second one has bounds from q to 2. So minus the limit as r goes to 0 from the left. This becomes 1 over r minus 1 over negative 1, so plus 1 over 1. So plus 1. Minus the limit as q goes to 0 from the right of 1 over 2 minus 1 over q. All right. Well, no issue with the 1, no issue with the 1/2. But what's going to happen here to each of these is a little bit different. Well, very similar actually, but it's going to look a little bit different with the with what's going on with the our one-sided limits here. So if we look at 1 over r, so let's say here's the r-axis. 1 over r looks like this. There's a vertical asymptote at r equals 0. So if we go to 0 from the left of 0, that means we're going towards 0 from this direction. So on this function, we're going to plunge down to negative infinity in this case. So we have essentially negative infinity plus 1 minus, what's going to happen here? Well, here we are approaching q equals 0 from the right of 0. So if we just make this our q-axis now, our function 1 over q looks the same as 1 over r. We would just be approaching from the different direction, from this direction. So this means we would go up to positive infinity. So this becomes minus 1/2 minus positive infinity. But when you look at everything, we're going to have the double negatives here and here. So we have negative 1.5 minus infinity, which is just negative infinity, which means the integral diverges.